right. Good afternoon, everyone. So welcome back to EE4210. So last time we sort of finished our discussion on the transport layer. So what we will do today is move on to the next layer, which is the network layer. So as we have done for the previous, transport layer, our goals here are again similar. What we would like to do is understand what are some of the functionalities that are provided by the network layer. We also want to know what are the principles behind those services and give us an idea about what are the things that the network layer is supposed to give us. And then once we know what are the functionalities that we need, we will look at some of the possible ways of designing or achieving those functions. And then we'll go on to real-life protocols and see how they're actually done in protocols that are actually implemented in the internet. All right. So in terms of the overview for today and I guess next Wednesday maybe, what we will look at is we'll start off with an overview of the network layer, and we'll see there are two basic things that the network layer provides. That one is called forwarding, the other is routing. And they're actually implemented in something called the data plane and the control plane. So once we have looked at these basic functionalities, then we will dive into, the routers are the ones where the network layer is mainly implemented, or it's implemented everywhere, but routers are the ones that carry the bulk of the job related to the network layer. And then maybe we'll get started on IP, the Internet Protocol. Hopefully we'll get to talk a little bit about the format of the IP packets and then IP addressing. And then what I would also like to do today is, last week I think I uploaded some of the tutorials. So maybe if we have time, we will do tutorial 1, and I'll go over the solutions for tutorial 1 today. All right. So let's talk about the network layer and what are the things it does, right? So the network layer's basic job is to provide to provide the path that needs to be followed in order to go from a particular source to a particular destination, right? And in order to achieve its job, just like with any other layer, what we do is we take whatever the upper layer gives us, put it in the form of a packet. And which that basically means whatever the upper layer gives us, we treat it as the data that we need to forward. But in order to get our job done, we may also add some additional headers and stuff. So essentially, whatever transport layer has given me, it will include IP header, UDP, TCP, whatever it was. All those headers are part of what this transport layer is giving me. But ARM network layer, I don't care. Whatever transport has given, I think of that as the payload that I need to send to the other side. And in order to figure out what is the path to be taken, any other functionalities that the network layer provides, it needs to tag on its own headers to it. Okay? And on the receiving side again, the reverse operation, the network layer, when it receives the packet from the link layer, it will strip off whatever network layer headers are, and it will give it to the transport layer. One of the things that we had mentioned earlier is that the application and the transport layer are only at the end hosts, right? So the end hosts will implement all the 5 layers: application, transport, network, and so on. But the routers in the network only implement network layer and below. So if you look at that, the network layer is common to everything and every device in the internet. Every device in the internet has to implement the network layer. There is some exception to it, and that will be when we talk about Ethernet switches and Wi-Fi access points. They are what we call layer 2 devices. They only implement the physical layer and the data link layer. They don't implement the network layer. But other than that, every other device in the internet has to implement all 3 layers. And as you send maybe I'm the sender, as I pump my packets into the network, the routers, they operate by looking at the network layer headers and then so on. So at the router in the network, so let's say if I pick any one particular router, let's say this guy, when it gets the packet, if you think at what's happening, oh, I turned this guy off. I should be touching this one. Don't need red. Okay. So let's say this is my laptop, right? And it is connected to a router, to a destination somewhere. Right? Here, my application created the data. Right? So this is at the application layer. Gives it to the transport layer. The transport layer will add its own headers. Let me make it green, let's say. And then it will give this whole thing to the network layer. Network layer will add its own headers. This guy had its headers. And then we will give it to the, what am I calling it, data link layer? Yep. And in order to do its job, the data link layer is going to add its own headers. Right? And let's say this whole thing has now come up to this particular router. This router also implements the data link layer and the network layer. And of course, there's a physical layer below. Right? The packet will first go up the protocol stack. The physical layer on this particular link will receive the packet, give it to the link layer. The link layer will say, all right, let's see. I guess the first one was the black one, and then the green one, and then the red one. The data link layer at the router will say, okay, I am done with this. The job of the link layer is done. So when it gives it up, it will strip off the link layer header. Right? And so we just have the green and the red part. Now this router's job is to figure out if there are multiple links connecting to this router, where should I go? And in order to do this, it will look at the network layer header. It's not going to look at any other layer. Okay? So the router's job will only be based on what is written at the network layer header. It doesn't look at whether it's TCP or UDP. It doesn't care about any of those things. And once it has figured out which way to go, it will again pass the packet downwards to the link layer and then to the physical layer. And while the packet is at the router, it can change the header for the network layer. So when the packet goes down and goes out, let's say on this particular link, the network layer headers may change, and actually they will change. Okay, the router can modify the header. All right. Sorry, it's taking time. Yeah. And that's what you see. The network packet goes up and down and all the way up to the destination. Okay. So in terms of the functions that the network layer provides, there are two things that any network layer, that means every router or even your own device will provide two things. One is called forwarding, the other is called routing. So in a typical router in the internet, it has many wires coming in, it has many wires going out, right? So if I were to zoom in here, let's say this is my router. It has many incoming links and many outgoing links. Let's say a packet has come in here. what do we usually do? We will take it and store it in the memory of the router, right? And then we will examine the header to figure out where you need to go. So that decision, should I be sending it here? Should I be sending it here? To choose the appropriate outgoing link, that's routing. Selection of the link where I need to send it. Should I put it on 1? Should I put it on 2? Should I put it on 3? That process of making that decision-making process is the routing process. Now, let's say my routing protocol says, oh, this particular packet which came in, and let's say it wants to go to some particular destination, needs to go out on 3. So somehow I have to connect from here, or at least move the data from this memory to this 3. So in some sense, I'm creating a physical connection between this incoming link and this outgoing link, or effectively I'm moving the packet which came on this link and moving it here. That process of moving the packet from one link, one incoming link, to an outgoing link, that's forwarding. Okay? One way of thinking about routing and forwarding is, imagine what happens when you take a physical trip. Maybe you want to go from this thing, let's say you want to go from NUS after the class. Let's say you are going off somewhere for the weekend, so you want to go to the airport, right? So what you could do is you could go to Google Maps or any other mapping software you have, and you say, I want to start at whatever, let's say the Techno Edge canteen, that's what I did here, and then I want to go to Changi. And then it tells you which path to follow. That's routing. It tells you how to go. But then along the way, you may hit roundabouts like this, right? It's just one right here in front of Yusuf Ishaq house. So maybe you came in here and you have to get out somewhere here. How will you go? Right? In this case, it's quite easy. I'm going to drive, leave the first one, leave the next one, and then get out in the third one, right? But there's a rule that says this is the road that connects me. And the process of going from this interface to this interface is forwarding. Now here it's quite very simple. So here's a fun picture for you. And this is a real life thing somewhere in England. And to be honest, I don't know how to drive here. This is too complicated for me. But the point I'm trying to make here is that even when it comes to routing in the internet, right? So you may say, how difficult is it to move a packet from here to here? Come on. Yeah. How difficult is it to move a packet from this incoming wire to this outgoing wire? Turns out it's quite challenging. Not because of, we don't know how to connect. It's challenging because you don't have much time. Imagine this is a 1 Gbps link, right? And let's say you want to provide a end-to-end 1 Gbps. So here, even if you have a very small packet, let's say 100 bytes, packet coming in, the amount of time you have till the next packet comes in is very, very small. It's in the order of a few nanoseconds maybe. So within a few nanoseconds, you have to move the packet from here all the way here. So in that time, you have to decide, okay, I have to run my routing algorithm. Or maybe I have pre-computed my routing algorithm and have stored the decisions in a table. I have to look up the table and then quickly move the packet from here to here. That's the challenging part. When you want to do this at a very, very high data rate, you have on the order of a few nanoseconds to do it. All right. So now let's look at these two things from another perspective. So we talked about forwarding and routing, right? So forwarding was to physically move the data from one incoming link to another outgoing link. We also call this operation to be done in quote unquote the data plane. This is the plane, all right. This is the realm or the world where data goes from one side to another side. So data plane takes care of moving data from one incoming link to one outgoing link. And it also determines exactly how I am operating this inside. So maybe I'll jump ahead a bit on this guy. Oh, you guys should tell me that I didn't switch. Yeah. So the data plane determines how we move data from one input port to another output port, right? So that's the physical. And how did I determine if a packet coming in and wants to go to California, which of the outgoing links I should choose? That's the routing protocol. That's sort of the brains behind the thing, right? That determines which outgoing link. That is called the control plane. Right? So the control plane determines the logic that we will use to find the path itself. And the data plane does the actual job of moving the bits from one link to another link. Right? That's one way of thinking. And even if I think about the data plane, right, and I say, okay, is it very difficult to do this? If you look at how I can move my data from one input link to one output link, what are my options? The simplest thing that we have talked about earlier is store it in the memory and then read from the memory. That could be one option. Other options include maybe inside the switch, I will have a single bus. Right? Just like you have buses inside your computer, PCMCI bus and all those things. Maybe I'll have a common bus to which everybody will connect. And I will just put my packet in this bus with a little bit of header. So this guy will also have to add a small header saying, oh, you need to go to 3. And then from the bus, it will pick it up. But then this bus has to operate, if these are at 1 Gbps each, this probably needs to operate at 3 Gbps. Otherwise, it will not be able to handle all of them, right? Everybody is sharing it. So that also becomes challenging. And in real life, the routers, the likes of Cisco and Juniper, Huawei maybe they sell. They sometimes use this, though it's sort of getting out of fashion. This is very slow in general. So they may use this, or they may use some kind of a fancy interconnect structure. Let's say I have 4 incoming links and 4 outgoing links. We may have a structure like this, which is like this is called a crossbar. We are not getting into all of this, but I'm just giving you a high. So there may be a very complex interconnection network that needs to be operated. And that's why switches are also pretty expensive. Okay? So the data plane, even though the name sounds very simple, just move the data from one port to another port, in reality, to physically implement that function, it's not simple. And the main challenge is, again, speed. All right. Now I remember what to do. Okay. So let's say I have taken care of my data plane. Packets come in, and I have some kind of an architecture that will move the packets from one input to another output. Let's talk about the control plane a bit. So the control plane's job is really to, if you tell me where you want to go, I will put you in the best path to go to your destination. I figure out the best. Best could mean the shortest path, could mean the least congested path, even though it's longer. Right? So you can define whatever you mean by the best path. But if you give me your definition of what is best, I will give you an algorithm that will calculate the best path for you. And that's what the control plane does. Now, even within the control plane, the way we would implement this control plane, or this way of calculating the best path, there are 2 approaches. There is the traditional approach, and then there is the newer approach, which is becoming popular and sort of becoming the standard, is what is called software-defined networking, or SDN. So let's talk about these in a bit. So let's talk about the traditional way in which the control plane exists in every single router. So what happens here? So of course I have my, let's say this is the way my networks, my routers are interconnected. Okay? So every router will also implement its own routing protocol. What that routing protocol will do is, the routers will talk to each other, and then they will exchange some information among them. On next Wednesday when we come back, we will see how these, what kind of information these routers may exchange to figure out. But they will talk to each other. They will tell each other things like, oh, my link here has, this much capacity. Oh, my link is congested. But whatever it is, they may talk to each other, and then they will figure out the best path. And every router will create a table called the forwarding table or the routing table. This table would look something like this. It would usually have, it would look at where do you want to go. Destination, address. And it will say outgoing link. So let's say I have a router like this. Maybe there is only one incoming link, and maybe there are 4 outgoing links. And let's say my addresses, let's say in my universe, there are only 8 computers. So I can address everything using 3 bits. The first computer is 000, 001, 010, 011. These are the 8 computers that exist in my world. So what I would do is, I would have an entry for every one of these. These are the 8 possible destinations where any packet may go to. And then for each one of these, I will say, oh, somehow my routing algorithm has to do this. And say, oh, if the packet wants to go to 000, we should send it out on link number 1. If the destination is 001, maybe it needs to go to 4. Maybe this is 1. Maybe this is 3, 2, 2, 2, 1. Something like that, right? So this is called my forwarding table or routing table. So this is the main job of the control plane. Compute this table. And in order to compute this table, again, we have 2 options. One is the per router one or the SDN one. In the per router one that I'm showing here, each router is running this routing algorithm, and it periodically exchanges messages with its neighboring routers or maybe everybody else in the network, and it computes its own routing table. Similarly, this router will compute its own routing table, and so on. Okay? And this is just to show that the routers will talk to each other, exchange messages with each other, and figure out what is the best way to route. And this is how things were done traditionally. However, this has certain challenges. One is, your routers continuously need to exchange messages and so on. Maintenance, upgrading, and all these things were very difficult. Occasionally in your network, some of the policies may change. If you change your policy, then you have to go and change the algorithm on each and every single router so that the policy can take effect. Very tedious. Sometimes you make mistakes. So currently the approach is that to say, okay, so this is the data plane. So currently the approach is this. I will have one single computer in the world, in my network, and that will be responsible for computing the tables for everybody. And that single controller, once it has computed the table, what it will do is, there are agents in every router, and the remote controller will communicate with these agents and send them the table. So as a router, I'm not responsible for computing the table. I just have an agent. It talks to the central controller, says, give me my table. And then it gets the table from there. And every router, the table gets populated. With the centralized approach, life is a little bit easier. And things are simpler. So all your modern day networks are usually based on SDN, and even networks such as 5G, they all use SDN to configure and operate. Okay. Another thing that I want to highlight here is the separation between the control plane and the data plane. So here I have a line that sort of breaks down where the control plane is and what the data plane is. So in the control plane, what happened is we run the routing algorithm. The routing algorithm at one particular router, even in the centralized case, the centralized algorithm may figure out somehow what the routing tables should be. But once the routing tables are computed, they are pushed down to the data plane. And the data plane stores these routing tables. Why? Because when the packet comes into a particular input link, I consult this table and figure out where I should place the packet. And the need is, these things need to be done very, very quickly. So I store everything at the data plane, so I can do the lookups very, very quickly. So even though the routing table is computed by the control plane, ultimately it is used by the data plane to do the forwarding. Questions? Yeah.
You mentioned for the forwarding table, like we have the header and the network link output. It's not uniquely like linked to the header, is it? Like for
You mean this one? Sorry, it's just slow. Come on, yeah. So this is my forwarding table, right? Okay, so what's the question then?
my question is that for each different address destinations, they don't go to like unique output link. They can go to the same link. For example,
Yes. So for example, these three, they all go to the same output link. Why, right? Okay, so let's come back. Okay, let me draw a topology maybe. So let's say I am here, and this is the router. So let's say this is 1, 2, 3, 4. And there's some router, and there's here, there's a router, it's here, and I say 2 here. So in this case, the way I have drawn my network, end hosts with address 100. So you can think of this as the IP address, the address of the computer. So in this case, computer number 100 with the address 100 is here. Computer 101 is here. 110 is also here. So if a packet comes at this particular router, it's consulting this routing table. So if you think about it, whether it's for 100, 101, or 110, in all three cases, I should be sending this way. So that's why for each of these, the outgoing link I need to use is 2. Is that what was that your doubt, or did I not answer your question?
Yes, it's answering the question. I thought like each one have one unique.
No, it just basically says, so for example, imagine I'm Singtel, right? So let's say this is Singtel. Anything that goes, so Singtel doesn't have so many wires, right? It may have one wire going towards North America, one going towards Europe, and so on. So anything in North America, the router at Singtel will say, use the link corresponding to North America. And there are millions and millions of computers in North America. They will all use the same link to go towards North America. So in my routing table, there'll be many, many, many destinations that may use the same link. Other questions? Yeah.
For the question regarding the multiple sources connected to a data bus, and we had to, like each
Data bus, this one.
yes,
Ah,
the one with the cross grid and
this one.
yeah, and
This guy.
yeah. Why are we using the link rate to be 3 Gbps?
Okay.
Because if I'm not wrong, like anyway, only one host uses the link at a time, right? Otherwise, if multiple were to use it, collisions would.
All right. So let's consider this guy, right? In this particular link, I am getting data at 1 Gbps. This link, 1 Gbps. This link, 1 Gbps. So ideally, I want to be able to send out data at 1 Gbps at the outgoing links also. Otherwise, this guy is going to back up and slow down. So any packets that come on this, they will use this bus, let's say, to go to their destination. Anything that's coming on, let's say, in this and wants to go to the destination, it's going to use the same link. I don't want anything to slow down. If this is also operating at 1 Gbps, what is the total rate at which data is flowing in here? From the 2 links, it will be 2 Gbps.
But can you flow it at, like can you flow it concurrently? Because
If it is a single bus, that means you're all sharing the wire. So in one wire, you cannot put 2 things at the same time.
yeah,
So cannot. The only way you can do this is you operate this wire faster than these wires.
so the problem with this implementation is that
This guy, somehow your technology should be, this should operate at n times faster than the links themselves.
so is that the complexity behind why it does?
So that is one of the reasons why this is challenging, right? Because already running at 1 Gbps or 10 Gbps is challenging. And if you have 20 of these links, you have to run the bus at 20 times whatever. So that's not so easy. Yeah.
Except for the issue in the bandwidth, which has to be n times the input data. Are there any issues with this system?
The other thing is that you're adding some extra things. So here, when I put things in a bus means so imagine the air around this is a bus. Right now I'm talking and it's for all of you. If it was just for you, how would you know it's just for you? I have to add a special tag in front that says it's for you. So even when this particular link sends out a packet and needs to go out on 3, so in front of the data, I have to add a tag that says 3. Because this will read it, this will read it, this will read it. A bus, by default, is broadcast. So all 3 of them are reading. Whose is it? So I need to have a tag. So that's an extra overhead I need to add.
But even in case of a single input, when there's only one data link input and there are multiple outputs, we still need that tag.
You will need that tag.
So
You will need that tag. All right. I switch. Where did all of these? Okay, so now that we have looked at the basic functionalities that the network layer is supposed to provide, which is forwarding and routing, so now let's look at what other services that the network layer can provide us, right? So in general, what are the things I could potentially ask the network layer to give? You know, when you're putting up a list of requests, of course you can imagine whatever you want, right? There's no limit. So kind of things I could ask the network to give me would be like, can you guarantee delivery for me? That means, can you guarantee that you will not lose any packets? I could ask the network layer, hey, network layer, can you be such that you will not lose any packets for me? That could be in my wish list, right? I could also have a wish list or a requirement that can say, how about a delay guarantee? Can you make sure that you will get my packets across within, I don't know, here I say 40 milliseconds, right? So the kind of services I can ask the network layer could be in terms of loss guarantees or delay guarantees. I could also ask, can you ensure that you will provide in-order packet delivery? So once I start pumping packets in the network, can you routers somehow work together so that you always provide in order? So packet number 1 always before packet 2, then packet 3 and so on. Right? Don't reorder my packets. I could also ask things like, make sure you give me at least 10 Mbps, some minimum bandwidth guarantee. For some applications, it may also be like, if I am pumping in packets, 1 packet every second, can you make sure that at the output also the same spacing is maintained? So the output also gets 1 packet every second. So there are all these kinds of things I could ask, right? So what does the network actually provide? The actual internet provide? Does it provide any of these things? The answer is no. Right? So the actual internet protocol, actual network protocol that is implemented in the internet doesn't really provide any of these things. It is what we call best effort, which says, you give me a packet, I will try my best. But I will not provide you any guarantees. I may lose your packets, I may reorder your packets, I may delay your packets. If you want any of those things, do it yourself. That's why we have TCP, for example. So as far as the network layer is concerned, it doesn't provide anything. And there's a reason or a philosophy behind this. Okay? And the philosophy behind this, at least you have to think about it a bit historically. So all of these started back in this, mostly in the 70s, right? And at the time the philosophy was, we want to keep the core of the network as simple as possible. We don't want our routers to be overwhelmed. As such, computing wasn't that great back then in terms of computational power, memory, even bandwidth, right? So you remember when we were talking TCP and reliability, or in general reliability, we have to do this sequence numbering, acknowledgements, and so on. So if you ask the routers to do that, it's going to be very, very complicated. They'll slow down considerably. So the philosophy was, keep the routing and the core of the network as simple as possible. Anything fancy, anything extra you want, let the end systems handle it. Let the computers at the very end, let them do whatever they want to do. As far as the network core is concerned, we will keep it simple. So that's why the routers in the internet just do best effort. You give, it'll try its best, but nothing beyond that. Okay. So now let's jump and look inside a router. So we know that a router is supposed to do two things for us. It's supposed to do forwarding and it's supposed to do routing. Let's see how that is actually implemented. So this is a very high-level overview of a typical router. And here, there are basically 4 components on this one. You have your input ports, you have something called output ports, and since we are using the word ports, I want to highlight that these ports are not the same ports when we say sockets. Completely different. Right? This has nothing to do with your sockets and port numbers and so on. It's just terminology. A port is, historically, what is a port? Where ships come and so it's sort of borrowing from that terminology. So this is a port means this is one place where links come in and connect to the router. And that's what it is. So you have input ports on one side, you have output ports on another side. And in the middle, you have what is called the switching fabric. So what is the switching fabric? This is basically this. Oh, come on. It's switching from one source to another source. So this here is the switching fabric in this case. So in this case, the switching fabric is the bus. In this case, the switching fabric was a shared memory. In this case, the switching fabric is a crossbar where we have multiple connections. So in the middle, you have your switching fabric, which takes care of actually interconnecting the input ports to the output ports. And then the 4th component is the routing processor. So the routing processor is the piece of software or whatever it is that calculates the routing tables for you, the forwarding table. And so if you were to draw the demarcation between the data plane and the control plane, it will be that horizontal line there. So the routing processor basically is your control plane, and the ports, the fabric, input and the output ports and the fabric, they are your data plane. Another thing which is important to know is how they are implemented. The control plane is implemented in software, where the forwarding plane is implemented in hardware. And the reason is, these are operating at Gbps or tens of Gbps. They need to be very, very fast. So if you want to do things fast, you do it in hardware. You build specific custom-built or purpose-built soft hardware that will do things very, very quickly. However, if you have calculated that forwarding table, right, that doesn't need to change very often. Most of the time, once you've computed, you're probably done. Periodically, maybe you want to change it. Maybe if you worry about congestion and other things, maybe periodically you recompute your forwarding table. You don't do it every nanosecond. Maybe every 5 minutes, maybe something of that order. So this part can be slower. So this part is done in software, which is usually, so previously, for example, we did checksum. You can do checksum using software. You can also build registers and other things which will do the addition and all those things for you. That will be about 100 times faster, roughly, somewhere in there, right? So implementing something in hardware is always faster, but more expensive. So that's the reason routers are so expensive, one of the reasons. Of course, the other reason is Cisco and whoever, they like to make money, so it's expensive. Yeah. Okay, so let me erase this thing here. All right. Now, let's come back. This is the routing processor, and this is the one that is computing things, the forwarding table. Once it has computed the forwarding table, what it does is it gives it to every input port. And we store that thing locally here. Why? Again, if you get a packet, you look at the header, you see, oh, this is the destination. Where do I go? you have to consult the forwarding table. If the forwarding table is stored in a memory somewhere else, you have to access that memory, get the result, takes time. Even nanoseconds are important. So every port is given its own local copy, which it stores in its own local memory. So the lookups can be done fast. All right. So let's look at the input port functions in a little bit more. Let's see what are the things that the input port provides. So if I zoom in into the input port, there are these three things. We first start with the line termination. What does line termination do? So imagine this is an Ethernet cable. So my line terminator is here. It basically takes the electrical signals, in this case, and the electrical pulses, let's say 0 volt, 5 volts, and so on, and converts them to binary things. Even if I had a wireless thing, my antenna would be sort of the line termination. It would convert from the electromagnetic waves that it gets, it will do the demodulation and whatever, and convert them to zeros and ones. Next, we have the link layer protocol. So in the case it was wireless in my laptop, this would implement Wi-Fi or IEEE 802.11. If it was a wire like this, it would implement Ethernet. Okay? So the link layer protocol would be implemented here. So you can think of this as the physical layer, this as the link layer of that particular link. Yeah.
In the previous slide,
Mm-hmm.
when the routing processor communicates with the switching fabric, why can't we just send the forwarding table there? And why do we need to send it to individual ports?
Just to make it faster. If you just keep one central thing here, when the packet is here, it will have to look up this table, get the result, then connect like this. If I give everybody their own copy of the table, of course it's more expensive, but it's much faster. It's like a cache that I give to everybody.
And what does the routing processor send to the switching fabric?
A table like this. If the output IP address of the output is this, use link number 1. This is what the routing processor computes, and this is what is given as the table that is stored there.
But it sends this to the switching fabric as well?
No. This thing is stored at the input ports. All right. And now, at the end, we have a queue or the buffer. So this is where packets that come in from that particular link, they are stored temporarily. And then we look up the routing table or the forwarding table, and then we determine which output link you need to go. Usually what is done is, there's a name for this, we say match plus action. So I see what output link you need to go to, and then once I find a match in my table corresponding to that output address, I take some action. What is that action? Usually I will connect you to that particular output link. But there may be other actions also. Sometimes, you may decide that, I have blacklisted this particular IP address. So this packet needs to be dropped. So those kinds of actions may also be done, but in most cases the action means just send it to the right place. Another thing is, there is a possibility that queuing may occur. Even though if I go back here and I say, let's say I'm using this as my switching fabric, the bus as my switching fabric. Okay? I'm using the bus as my switching fabric, and the bus operates n times faster than the incoming links. Right? I have like this. So incoming links are 1 Gbps, my bus operates at 3 Gbps. Then you may say, no, there should not be any problem. As soon as a packet comes here, I should be able to send it out to the output. The answer is no. There may still be a problem. What could be the problem? So let's say, let me draw it again in a cleaner fashion, right? So let's say I have this bus. This is running at 3 Gbps. And I have these 3 incoming links, 3 outgoing links. Let's say I get a packet here. It wants to go to output link number 3. What if at the same time this guy also gets a packet which wants to go to 3? Then, even though I operate this at 3 Gbps, this guy cannot handle 2 things at the same time. Right? If 2 packets want to go to the same destination, cannot. Only one of them will get the chance. And the switch has to make some kind of a decision. Should I let this guy or should I let this guy go first? But whoever it picks, the other person has to wait. Right? So that is one kind of blocking. Another thing could be that, let's say there is already a queue built up, right? And the next packet here, just behind it, wants to go to 2. But the first packet here in this particular queue wants to go to 3. Here also it wants to go to 3. And let's say the switch picks this one. If this wasn't there, 2 could have gone here, 3 could have gone here. But just because the guy in front of you doesn't want to move or cannot move, this packet that wants to go to 2 is blocked. That can also lead to queuing. Right? So just because you are operating your system at a higher speed doesn't always mean you will be able to make it. Okay? So there are other complications. And this is one of the reasons why you may have queuing and packet losses and things like that. And when I do this forwarding, when I make the decision as to which output port you need to go to, holistically saying, there are 2 options we can do. We can do destination-based forwarding, and that is what is done in most cases. We just look at which is the destination address you want to go to, and then I forward you. And, theoretically, you can also do generalized forwarding. This basically says, in addition to your destination address, I will take into consideration other factors. For example, this may be your shortest path, and usually I will give it to you the shortest path, but maybe this link is very congested right now. So I will send you on another one. So you can, add more and more things, and you can generalize it as far as possible. Now let's look at this forwarding table in a little bit detail. I did a toy example there where I said there are only 8 computers in the world. So my addresses were from 000 to 111. And what I did is a table with 8 rows in there. It's okay. 8 rows is not too bad. But then in the real world, there are much, much more than 8 computers. And in the old days, addresses used to be 32 bits. So with 32 bits, how many possible addresses you have? 2 to the 32. That's about 4 billion, roughly 4 billion. So if you were to do a naive approach like I did, where you had 1 row for every IP address, your table would have 4 billion entries. And that table would have to be recreated in every one of these input ports. So every one of these input ports would have a table with 4 billion rows. 2 problems with that. One is, of course, you would need so much memory. Right? Gigabytes of memory. Not very easy to do. Another thing is, your lookup will be very, very slow. When a packet comes in with a particular IP address, what do you got to do? You got to go to your table and see where is the match, which row I have the match. So you have to look up through 4 billion entries. That's going to take a long time. You definitely cannot do it in nanoseconds. So what to do? The solution to that is done by the way we allocate these IP addresses. You cannot pick any arbitrary IP address you want. Just to make the life of the routers easy, IP addresses are allocated in a very, very structured way. Okay? And we will talk about that. In general, wouldn't it be nicer if instead of having a single entry for every IP address, so now I have switched from 3-bit addresses to real-life 32-bit addresses, right? So instead of having 4 billion rows here, wouldn't it be nicer if I could say, oh, everything in this range, if your IP address is in this range, you just need to go to output link 0. Another big range, if anything in this range, you just go to 1. Anything in this range, you just go to 2. And if anything else, we go to 3. If we were somehow able to do these ranges, then my routing table will be much, much smaller. And that's the whole idea behind how we allocate IP addresses. We allocate in a very hierarchical way. So IP addresses that look together or that are sort of common will be geographically in a single location. So the routing becomes much, much more simpler, and we don't have billions of entries. We just have entries corresponding to each range of addresses that works. And our routing tables will be like this. They will say this range of addresses, pick this output link, this range, go to this output link. But the way they are actually written down is not like this, something, something, through something. The way we actually write it looks something like this. We just write the common bits in that range. If I go back here, the common bits are here, right? In this range, these bits are common. The most significant, whatever number, 16, 17, 18, 19, 21 bits are common. So the way I will write it in my table says the first 21 bits should be this. The remaining I don't care. As long as the first 21 bits are this, go to output link number 0. This particular range, let's see. The first 24 bits are common, right? And the last 8 bits are different. The way I will write it in my routing table is, as long as the first 24 bits are this, the remaining 8 bits are wildcard, I don't care, go to 1. Okay? So my routing table will be like this. So when a packet comes in, what should I do? I need to see where there is a match. Let's take an example because there's a subtlety here. There's a small thing we need to look at. Let's look at this particular destination address. DA stands for destination address. Right? Right? So in this particular address, first 1100, 1 then 3 zeros. This is okay, this is also okay, all 3 of them match. Then if I look at the next 8 bits, again all 3 of these match. So far everything matches, right? Then I see the next 4 bits are 3 zeros and a 1. That's also okay, that's also okay, that's also okay. Then I have 0, 1, 1, 0. This is okay. This is not okay. This is not okay, right? So in this case, it's obvious that there is a match here. So this particular will go to interface number 0. Let's look at the next one. In the next one, again, it's quite similar. So the first 16 bits are the same, right? So they will match with everyone. Then I have 0001. That's also a match with everyone. But then I have 1 followed by 3 zeros. That matches here. It also matches here, right? Because the rest 3 here stars, anything is okay. So now I have 2 matches. This is okay here, this is also okay here. Which one should I pick? The way we do this is something called longest prefix matching. So these are sort of the prefixes, the first part of your address. If you have more than one match, you will pick the one with a longer match. And here, that will be here. Here I have a longer match of 24 bits of the prefix. And here I only have 21 bits of the prefix, which is matching. So in this case, this is going to go to 1. And in case nothing matches, of course, there's this default otherwise thing. Questions? All right, so now the last one here is our output port. An output port is just like the reverse of the input port. So we have queuing, we may have a buffer there, and then followed by the link layer protocol, and then followed by the line termination. Right? And again, when we have buffering, like this here, why would I need buffering? Because, depending upon what kind of switching fabric you're using, it is possible that you may get data at a higher rate than the rate of the outgoing link. Right? So maybe the switching fabric is operating 10 times faster. So maybe you can get 10 packets per second, but the outgoing link is only 1 packet per second. Right? So in that case, you would have to queue up. And again, if you have packets queuing up, how should you send them out? The most common way of doing that is first come, first serve. Right? The oldest packet will be transmitted first, but that's not necessarily always true. Later on, when Professor Tefek comes in and he talks about multimedia, there you will see that it is also possible to use scheduling disciplines. So for example, different packets may have different priority. So in that case, you will take a higher priority packet and send it out. But by default, all routers in the internet do first come, first serve, or first in, first out, same thing. Whoever comes in first will be taken out first. And since we have queues at both the input port and the output port, as a result of having this is the fact that you may lose packets, you may have queuing delays. Right? So when I talked in the first few lectures that routers can have queues and can have queuing delays, so these are the queues where packets may pile up, and if you're unlucky and too many packets are coming towards you, at some point you will start losing packets. All right, so that was sort of a we talked about the internet protocol. What the network layer provides, the functionalities of the network layer, and we also took a look at what is inside a router. So let's see, 4, 5, or 6. Yeah.
For the high-level router architecture back on slide 14, you mentioned that each of the input ports have their own forwarding table and cache, right? If that's the case, what's the purpose of the routing processor interacting with the switching type, since all input ports?
So what it says, so maybe you have taken the arrow very literally. Let's draw it like this. It basically, so this arrow is supposed to say that the control plane is interacting with the data plane. So that's what the arrow means. It doesn't mean there's an interaction going on and it's storing it in the switching fabric. It just says control plane and data plane, they interact. And the interaction is control plane provides the data plane with the forwarding table. But that forwarding table is actually stored here.
So there is no form of logic in the switching fabric?
No. No. Okay. So I think this might be a time to sort of stop this part, and maybe we go towards the tutorial problem. Okay, I think logically this probably makes more sense. Come on, come on. What? Okay, so this is a tutorial problem that I had uploaded earlier. So let's try doing tutorial 1 today in the next 20 minutes or so. So the problem 1 says consider a packet of length L which begins at end system A and travels over 3 links to a destination end system. And these 3 links are connected by 2 packet switches, and let DI, SI, and RI denote the length, propagation speed, and transmission rate of link I for I equals 1 to 3. The packet switch delays each packet by some processing delay. Assuming no queuing delays in terms of DI, SI, and RI and L, what is the total end-to-end delay for the packet? Okay, and then the second part where it starts with suppose, it gives you some values, numerical values for the packet size and the propagation speeds, and then says what will be the actual value, right? So the way we can do this is let's solve it for the general case in terms of SI, DI, L, and RI, and then the second part is just plugging in the numbers and you'd be able to evaluate. Okay, so this is sort of what we have. We have A on the side, and let's say we have B on the side, and we have 2 routers in between. Right? And we are sending packets of length L. Right? Yeah. And the length of this particular link, this is D1, this is D2, this is D3, and the data rate on this particular link is R1, R2, R3, and the propagation speed here is S1, S2, and S3. Right? So now it says how long will it take for the packet to go from A to B. So again we remember that there are 4 components to the delay. Let's see, the transmission time, propagation time, queuing delay, and the processing delay, right? And these will appear at every router. And at the very beginning, it's just the transmission time and the propagation time. So we will start transmitting our data here. And in order to do the transmission, it's L bits at a rate of R1. Right? So this is transmission time. After that, the data has to propagate from A, let's say, to the first router. What is that propagation time? Distance over speed. Right? So this would be the propagation time. After this, my packet is now at the first router. At the first router, I can have queuing, processing, and all of this, but the question tells me that I don't really have any queuing delay. Ignore queuing delay, so I can cancel this one out. At the first router, I will have the processing delay, and then we're going to have to transmit the packet here. That transmission will take L over R2, and then it has to propagate all the way to the second router, that is and this is the transmission time. Once my packet has reached the third router here, the second router, again I have a processing time. Then the packet needs to be transmitted. R3, sorry. And then so on. Right, so the total time it will take for my packet to go from A to B is this. So that's the first part of the problem, right? And in the second part, it gives you basically values. It says, now say that the packet is 1,500 bytes. So L is 1500 bytes. And then propagation speed on all is 2.5 into 10 to the 8. 10 to the 8. Meters per sec, and then these are 5,000, 4,000, and 1,000. So the only thing you need to keep in mind is, the units. Be careful. What was it? 1,000. And the transmission rates on all the links is 2 Mbps. Just plug in the values here. The only thing I would like to highlight here is, so let's say R1 equals R2 equals R3 is 2 Mbps, right? So this basically says 2 into 10 to the 6 bits per sec. And here the packet size is given in 1,500 bytes. So you have to convert it into bits first. So make sure all your units match up, otherwise you'll get an incorrect answer. And if you do plug in all these values, this should come out to be, the whole thing should come out to be 64 milliseconds. Questions? Now let's go to problem number 2. Problem number 2 is very similar, but now we have packetization of the data, right? And it says we break things up into smaller packets and then send the packets into the network. But the network topology is exactly the same as we had drawn here, right? So there's a source and the destination, and then there are two switches or routers in between. And now it says consider a message that is 8 into 10 to the 6 bits long that needs to be sent from source to destination. Suppose that each link is 2 Mbps. Ignore propagation, queuing, processing delays. So life is more simpler here. All we need to care about then is transmission time. Right, so in this example, we'll only consider transmission time. So now it says consider sending the message from source to destination without message segmentation. Means no packetization, the whole thing in one go. Okay? How long does it take to move the message from source to the first switch? And then, using store and forward, what will be the total time to get to the end? That's A. And then B and C do the same thing with packetization, but now we break up the packet into break up the whole message into 800 packets, and each packet will become 10,000 bits long. And then we'll repeat this. So let's do this then. So again, I have this same topology, R1, R2, and B. Okay? And the way I will do this is using my time diagrams, which draw time in this axis. The time is going in this direction. At time t equals 0, I start my transmission at A. Right? And it says I can ignore propagation delay. So the first bit, as soon as I transmit, it will reach R1. Right? There's no propagation delay. But now I have to keep transmitting the other bits one after the other, till I transmit 8 into 10 to the 6 bits. Because in part A, I'm not breaking up into packets. What will be the transmission time? Packet size, or the size of the message. So L over R kind of thing, right? So here, the whole message is one packet, and R is 2 into 10 to the 6. So this is 4 seconds. So I go at t equals 4, I'm done transmitting. And the last bit immediately reaches R1 because propagation delay is 0 in this example or in this problem. Right? And this particular router is doing store and forward, which means if a packet is coming, you receive. Once you have received the whole thing, you have to wait. Now you can send it out again after consulting your routing table and whatever. In this case, that processing delay is 0. Queuing delay is also 0. So as soon as you have received your last bit, you can start sending the packet out. So at t equals 4, R1 can start sending the packet to R2. So the first bit of the packet will reach R2 again at 4 seconds, no delay. But then the first router has to keep transmitting the bits one by one. How long? Again the same thing, 8 into 10 to the 6, 2 into 10 to the 4. So this is also going to need 4 seconds. So at t equals 8, we will be done. And at 8 seconds, the packet has reached R2 completely. So now R2 can start forwarding it. And t equals 8, the first bit will reach B. But R2 has to keep transmitting it. The whole packet, 8 into 10 to the 6, divided by 2 into 10 to the 6. Again, this is going to need another 4 seconds. So at t equals 12, I'll be done. Questions? Yeah.
The R1, the transmitting rate is 2 × 10⁻⁶.
Yes, every one of these is 2 into 10 to the 6. Oh, okay, sorry. Yep, I wrote it wrong. Yeah, this is 10 to the 6. Thanks. Yeah. All right. So now this was part A, let's say. And let's do part B here. Let's say at t equals 0, we start again. Now, in this case, what I have is each packet, so I have 800 packets. And each packet is 10,000 bits. Right? So t equals 0, I start, and my first bit will reach immediately. But then I keep sending. How much time till I complete my first packet? Now this time it is 10,000 divided by 2 into 10 to the 6, which is 5 milliseconds. Right? This is seconds here previously. Now it is, let's say, 0.005. So at 0.005, my first packet has reached R1. Let's say this is packet number 1. So at t equals 5 milliseconds, R1 can start sending. The first bit will reach here at 005, but then it has to keep sending or transmitting the remaining bits. How long it's going to take? Again, 2 into 10 to the 6. The transmission time here again is 5 milliseconds. So I will be done at 10 milliseconds. Right? So after another 5 milliseconds, so this is 010, I'm done. At t equals 10 milliseconds, R2 has the packet, so it can start sending. And again, this will take 5 milliseconds. 10,000 milliseconds, right? So the first packet is going to reach the destination at 0.015. Yeah, I think this is what B is asking. How long for the first packet to be received? But now how about the rest of the things? When will the entire file be received? Right? In order to do that, you remember, if I look at A, at the source itself, it is done with the first packet at 5 milliseconds. At the time, it can get started on packet number 2. Right? So it can send packet number 2 here. This is going to get done at 10 milliseconds. And at 10 milliseconds, router 1 can get started on packet number 2. And this part is 15. So at 15, R2 can get started with packet number 2. And that will reach the destination at 20 milliseconds. And this whole thing will continue, right? Every 5 milliseconds, I can send out a packet. So this will be 3. This will be 3. This will be 3. And the third packet is going to reach at 25 milliseconds. I can continue like this. And at some point, I will send packet number 800. What will be this time when I send packet number 800? There are many ways you can do this. You can say, oh, 5 milliseconds per packet. So 800 times 5, this is 4 seconds. Or you can, realize that this is, again, I'm transmitting 8 million bits. To transmit 8 million bits here, it's 8 million divided by 2 to the 10 to the 6. Again, 4 seconds. So it's still, I'll be done at 4 seconds here. And at 4 seconds, if I start transmitting the last packet, at 4.005, packet number 800 will be at R2. And if R2 starts at 4.005, it's going to be done at 4.010. So at 4.010, the entire thing has been received. Yeah. It's 4.010. Okay. If you, yeah. The first packet, when did it reach? After 10 milliseconds. Right? No. Hang on. Yeah, the first packet was received after 15 milliseconds, but it is still 4.010. One way you can think is, when did router 1 finish receiving all the packets? At 4 seconds. When did router 2 finish receiving all packets? 4.005. This will receive after 5 milliseconds. So that will be 4.01.
The transmission to 800 packet begins at
995, yeah. Okay. So now you may ask, what happened? Here also, let's see if I can do this. Yeah. In the first case also, we finished at 4 at source. Here also I finish at 4. But here it takes 12, here it takes only 10 milliseconds more. And the way you want to think about this is pipelining. Here, for the entire 4 seconds, this link was sitting idle. But here for the most part, except for 5 milliseconds at top, while this guy was transmitting, this link was also transmitting. And this link was also transmitting. Here, because the packets were very, very large, while this was transmitting, nothing could go on here for 4 seconds. And nothing could go on here for 8 seconds. But if I break up my packet into smaller pieces, I can more efficiently use my resources in the network. That's another one of the reasons why we would do packetization in the network. Okay. So whatever I've drawn in the figure, that sort of takes care of the first three parts, A, B, and C. Now, part D says what are the reasons to use message segmentation. That means why do we want to use packetization? One, you see that it allows you to use your it allows you to use your links and resources more efficiently in parallel, right? I could use all three links in parallel at the same time for most of the time. When I had smaller packets. With large packets, I couldn't, with the whole message, I couldn't do it. Other advantages that you may have with packetization. Let's say I didn't do packetization. I sent the whole, how much was it? 8 million bits in one go. Even if link errors are rare, in 8 million bits, it's quite likely that 1 or 2 bits would be flipped here and there. What will you do then? There's an error. You have to retransmit the whole 8 million bits. Even if there's a single bit in those 8 million bits in error, you have to retransmit the whole 8 million bits. But imagine I have done it in packets. Now in 8 million bits, still the same one error. Now I just need to retransmit that particular packet of 10,000 bits. I don't have to repeat all the 800 packets, just one packet. So in the case of errors, it's much more efficient when you have smaller packets because you don't have to retransmit the whole big message because of one single error. What else? Oh yeah, another thing is, if you think about queuing delays in routers and so on, if you have a big packet waiting in front of you, it's like, one day I went to there's this desert thing, I think it's in science, and there must be a club thing going on there. Some guy came up with actually 60 orders of that desert thing. So I waited in line for about 40 minutes, just because my wife had asked me to bring, so I had to, there's no choice, right? I had to do. But it's like a big order in front of you, so you have to wait in the queue for a long, long time. So if there's a big packet in front of you, life is bad, you have to wait. But if packets are smaller, the delays would in general be smaller because you would get a chance to get in. What would be the drawbacks of using this? One is, of course, now you have 800 packets at the destination. You have to do some work to put them back together. Packetization itself takes time, and reassembly also takes some time. What else? In the way I drew it, 8 million bits, divide by 800, and 10,000 bits are going. But in real life, in addition to the data, you would have to add headers to the packets. If I send one whole thing, I just have 20 bytes of headers, let's say. But now I have broken up into 800 packets. Each one of those 800 packets will get its own set of headers. So it increases the overhead. So that could be one drawback there. Questions? All right, in that case, I think this is a good time for us to stop. And when we come back on Wednesday, we'll continue with our network layer discussion.